As we return for the second part of the session, let's take a moment to review what we did in the first. We spent the first session bootstrapping an IOU ring context. Inside of that IOU ring context, of course, we dealt with the vagaries of interoperating with the resource acquisition and disposal modalities of C. But simply creating an IOU ring context wouldn't have given us anything interesting. The purpose of an IOU ring context is to allow us to make asynchronous syscalls, and so we projected an API that does exactly this. Allows us to generically access any of the syscalls supported by IOU ring. But if we're going to have an execution context that gives us this power, we should have some way to use it from any part of our program, not just ones on the same execution agent. And so we gave it a way to vend a scheduler that can be used to get onto the appropriate thread to interact with this context. And of course, as the last session came to an end, we provided a way to delegate an execution agent to make forward progress on this context, to actually perform all of the work we carefully set up by interacting with all of its other APIs. But the fact that we went on this journey doesn't tell us why exactly we did this. Why was it that we decided to implement an IOU ring context? What were we hoping to achieve? And the way we justified this at the beginning of the last session is by saying that we wanted to asynchronously read some bytes. But there's many ways to read bytes asynchronously that don't involve bootstrapping a generic wrapper over IOU ring. And we justified this in turn by saying that we wanted to perform fewer syscalls than we would perform with the epool model. And now that we have access to IOU ring, if we throw into the mix submission queue polling, we have a way to submit syscalls to the kernel, potentially making 0 actual synchronous syscalls. But the fact that we wanted to read some bytes reminds us of something. It reminds us that at the beginning of the last session, what we actually started out doing was wrapping up a file descriptor. And we ended up with an API that looks like this. One where we can see that we have borne out our promise to realize readsum as an asynchronous function, because it returns now a sender. But if we think back to the beginning of the last talk, of the review I did after I wrote this code, I highlighted all of the glibc functions. I said that behind each of them was a syscall. And then we spent the entire session eliminating exactly one of those syscalls. But now we see another glibc function highlighted on the slide. The call to open buried inside the constructor of our file descriptor wrapper. But constructors have a special structure. We were able to make our function asynchronous by rewriting it as a sender factory, rewriting it so that it returns a sender. But constructors don't have a return channel. Constructors can't be made into a sender factory, and so how are we going to eliminate this call to a glibc function, which in turn makes a synchronous syscall as well? And maybe we hope that we can give this problem the runaround. Maybe we hope that perhaps IOU ring doesn't have asynchronous operations which support creational modalities. And so we go and we open up the Linux man pages and we start thumbing through the list of supported asynchronous syscalls, and we discover that IOU ring does. You can absolutely use IOU ring to asynchronously open a file and acquire a file descriptor thereto. With this source of hope having led to nothing, maybe we think to ourselves that we can gain support and comfort from the language feature that brings us asynchrony. Senders and receivers is a C++26 feature, but coroutines are a C++21, and so surely the people who standardized coroutines thought of this, and we can just crib their solution. And so we go instead and open up the standard, and we find the apropos part thereof. And we discover the solution that coroutines have to constructional patterns, which is to say by fiat that they do not support them. But in C++, we have access to creational modalities that aren't just a constructor. We can instead realize creation as a call to a static member function. And so we decide we're going to do that. We're going to reformulate our file class so it has a static member function that creates one, but which is asynchronous, which is a sender factory. Of course, we still need the shell of a constructor to bring our object into being, but it doesn't do anything. It just accepts a reference and accepts ownership of a file descriptor. The really interesting functionality now lies inside of that static member function, one we can see as a sender factory because it returns a sender. And herein what we have to do is wrap up an asynchronous syscall using IOURAII. But by now we are experts in doing that. We have a turnkey generic API that allows us to wrap up any of them, and so we go ahead and use it. We go ahead and say we want to perform an asynchronous syscall which opens a file descriptor beneath a certain directory at a certain path with certain flags and a certain mode. But as we reviewed in the last talk, that just gets us back a raw CQE. We need to adapt that to what our users want, which is an instance of our file class. So we attach a continuation that does this, which abstracts away the error handling and then returns an instance of file, satisfies the requirement that we asynchronously create this object. But while this benefits from guaranteed return value optimization, later on in the senders and receivers pipeline, this object will be moved around. And so we've given up something as compared to constructors. We cannot construct immovable types. But let's imagine for now we're fine with this, because there's actually another problem that is staring out at us from this slide. In the last talk, all we wanted to do was asynchronously read some bytes. When we asynchronously read bytes, we take bytes from the kernel and we copy them into our address space. Those bytes come with values, but they do not come with responsibilities. But now we are asynchronously acquiring a file descriptor. It has an integer value, but in some sense that is the least interesting part about it. But what it does come with is a responsibility to later call close with that same file descriptor to free the associated resources in the kernel. And so in this entire pipeline, we need to be absolutely sure that we never run into a situation wherein the kernel generates a file descriptor for us, but we drop it on the floor. But then we consider what's lying underneath what we're seeing on the slide. And what's lying underneath what we see on the slide is a call to externally completed, a generic algorithm, which we pass an initiate function which it has no particular knowledge of, which we pass a sender factory to it can use for cancellation, but which it has no particular knowledge of either. And so how exactly is externally completed supposed to know that the cancel operation it started did anything? How is it supposed to discriminate between the situation wherein it successfully canceled the main operation and the situation wherein the cancel was simply too late? But maybe that's too abstract. We should make it concrete. We should explore an actual example of what can happen. We go to our IOU ring and we submit an open operation. We want to open some file and get a file descriptor. But in so doing, we have entered the fundamentally racy domain of asynchronous operations. Maybe almost immediately that operation completes. Maybe it completes inside of the kernel, but the kernel hasn't posted the CQE yet. Maybe the kernel has posted the CQE, but we haven't regarded the completion ring yet. And in the interim, someone requests this operation stop. Externally completed becomes aware of this and goes to that generic sender factory and obtains a sender. A sender which it knows generically, if it connects and starts, will have the effect of canceling the outstanding operation. And so it does that, and that operation is now in flight. But then imagine we regard the completion ring. We regard the completion ring and we load the completion queue entry therefrom. This indicates that our outstanding operation has succeeded and has delivered to us a responsibility. The responsibility to dispose of this file descriptor. But of course we can't move on here. We can't move on here because structured concurrency demands that we wait for the completion of all of our nested activations. And we just nested within ourselves the activation of our cancel operation, and so we wait for that to complete. But now externally completed, a generic operation with no particular knowledge of these operations we've glued into it has a decision to make. Does it complete with set stopped or set value? And from externally completed's point of view, it did everything it needed to do to cancel that operation. It received the stop request. It obtained the sender. It connected it, it started it, and it let it run through to completion. And so maybe the implementation of externally completed decides to send set stopped. But if it does this, it throws away that file descriptor. It abandons that responsibility that the kernel gave to us. And what we're discovering once again is the fact that we didn't understand the complete interface necessary for externally completed. Because externally completed doesn't just need an initiation and a sender factory for cancellation, it needs also a classifier. some way that can examine completions of the main operation after a stop is requested and determine whether or not they actually indicate that stop did anything, whether or not they actually needs to transmit set value so we can obtain that resource that it is incumbent upon us to not throw away. But why are we responsible for not throwing away this file descriptor? Why do we care about this numerical value flying around in our program? And the reason for this is because it comes with a responsibility to dispose of it. But that opens a whole different can of worms. It opens this can of worms. It opens the can of worms of the fact that we have one glibc function call remaining, a call to the synchronous function close. And maybe once again we are filled with hope that perhaps IOUring does not support closed system calls. And so we go to the Linux man page and we find that that hope is fruitless. And once more, maybe we hope that the language has our back. We try to figure out how it is that coroutines solve this problem, but they just decided it wasn't worth considering. But I find that when you come to an impasse in software engineering, the thing you should do is just immediately figure out what you actually know how to solve. We don't know how to make an asynchronous destructor, but we do certainly know how to submit an asynchronous closed syscall. And so we decide to write a member function, which is a sender factory, which does this. But this is old hat for us by now. We all already knew what was going to appear on the screen. We're going to fill in the SQE. We're going to pass the invocable that does so through to syscall. We're going to have some then that transforms that CQE completion to how we actually want our asynchronous operation to complete. And here we suppose that closed syscalls always complete successfully. But on this slide is something subtle. On this slide is something subtle that is not unique to this slide. On this slide is something subtle that has been on every single slide in this session and the last one. And what I'm referring to, of course, is meticulous, rigorous attention to the correct annotation of functions with no except. And the reason for this is because cleanup shouldn't fail. Think about what it would mean if cleanup did fail. How would you follow up on that? You try and dispose of a resource and you're told, I couldn't. Are you going to retry? Are you going to end your entire program? How can you reason about the environment that you are left in? And so for this reason, C++11 makes destructors no except true by default. But here we're annotating regular synchronous functions with no except. We're doing so in an asynchronous universe. What we're seeing is that when a synchronous part is injected into an asynchronous pipeline, inspection of the no exceptness thereof predicates whether or not that asynchronous operation can fail. Let me give you an example. I have a very simple sender, just piped into then accepts an invocable which takes no arguments because just didn't send anything. It returns 5. This is an asynchronous operation that always completes immediately, successfully, and yields the integer 5. And at the bottom of the slide, we can see the completion signatures of that asynchronous operation. Barely, it only completes successfully sending a single integer. But why? How does then know that invoking that function doesn't throw an exception? How does it know that it in turn doesn't need to pass that exception on? And the answer to that is because it simply looks at the no except. It does generic programming to determine whether or not the error pathway is reachable. And we don't have to just suppose this is the case. We could just go ahead and modify the code. We can drop the no except, and now we see that then has learned about this fact and publishes out an additional completion. It says, I can additionally to sending 5, throw an exception asynchronously, complete erroneously, transmitting an exception putter. But now we have subtly introduced a completion path that makes this unsuitable for use in asynchronous cleanup. Because as we just said, asynchronous cleanup should not fail. And one of the results of this realization on my part is that I went on a bit of a crusade. I went on a crusade going through NVIDIA's implementation of studexec and fixing the exception correctness of all of their algorithms, fixing the exception correctness of connect, fixing the exception correctness of their published completion signatures. But I was not content to just limit this crusade to open source libraries. No, instead I also took this crusade all the way to the standard library, proposing papers which would enable standard algorithms to accurately perform these computations as well. But I've been saying over and over again in discussing this that cleanup should not fail. And that makes sense in the synchronous domain. Because in the synchronous domain, our taxonomy of completions has a cardinality of 2. We succeed or we fail. But in the asynchronous domain, there is a difference between saying something can't fail and saying that it must always complete successfully, because in the asynchronous domain, asynchronous operations can send, set, stopped as well. They can learn that their asynchronous forward progress is no longer required or desired and send, set, stop so they can complete immediately without doing what it was they would have done if they had completed successfully. But think about what that means for a cleanup operation. For a cleanup operation to complete unsuccessfully by saying it didn't think its forward progress was any longer required means it didn't actually do the cleanup. And so it's not sufficient for us just to go and annotate our code correctly with no except. We also need to make sure that asynchronous cleanup does not send, set, stopped. And if you think this is something that works cleanly across all of the asynchronous algorithms in std execution out of the box as adopted into the standard, you would be incorrect. Because I had to go on a different crusade as well. A crusade to ensure that asynchronous algorithms don't erroneously advertise that they will stop when they actually will not do so. But this is just how we implement our destruct member function. A member function which no one is under any obligation to call, which if being used would model the kind of manual cleanup we don't like in C++. And so we can no longer dodge the question, what do we write in that destructor? And given all the things I've said, given the fact that we understand how important cleanup is, maybe we can imagine that here in the destructor, where it's important the operation actually complete, is the one and only time we can avail ourselves of blocking semantics. Maybe we imagine that we can just wait for destruction to complete. But I don't have to explain to you why this is wrong. We explored why this was wrong in the last talk. It's only safe for us to interact with our IOU ring context from a single execution agent, and therefore that must be this one. But now we're preventing that thread from being used to make forward progress because we thought it was so important to make forward progress on a destruct operation that will now never complete because it is deadlocked. And so maybe we decide to go in the completely opposite direction. Blocking didn't work, so let's do something that's akin to super not blocking. Instead, we'll just say, well, I'm just going to let that destruct operation careen off in the background. After all, the object's lifetime is ended. No one can ever interact with it again, and so all I care about is that eventually this close operation is completed. Eventually that resource is released back to the kernel. Ruslan.
We didn't standardize this. Standard dash is not part of the standard. So it should be maybe still exec or something, but never mind, yeah.
So then you go and you actually write this code in your compiler. And it doesn't compile because we removed it from P2300 before we standardized P2300 in St. Louis. But I've given several talks that talk about asynchronous operations, how you can implement them generically and flexibly as a user on top of std execution. And so maybe we imagine that we're not going to let the standards committee get in our way. They chose to remove this needful functionality. I've discovered the place which needs it, and so I'm just going to go and write my own. I don't get to write std execution, but I can certainly write my own start detached and use it. Because after all, it's so important we clean up automatically. It's so important this destructor actually kick off that cleanup. But if we're going to add start detached to our library of asynchronous algorithms, maybe we should start by understanding how it's actually implemented. Maybe we can go and get an old version of P2300 and see how it accomplished that. And so we go ahead and do that. We go ahead and do that and see that true to its name, it does start an operation detached. It creates a new detached operation, and then it starts it. But as we look at this, we see something that makes us uncomfortable. We see something that every C++ developer hates. We see naked new. And even if we can convince ourselves this use of naked new is fine, because we're entering the structured concurrency universe and we know on the other side delete will be called, we are still allocating. This is not zero alloc. There's a performance overhead to calling new here, but there's something else as well that happens when you call new to allocate memory. And that's that new can fail. And so now in our cleanup, in our destructor, which we just reviewed rigorously, should not end in an exception or error, we have the possibility of an exception throw. And so, of course, we do what any reasonable person would do. We go back to our destructor and we rewrite it so it has a try-catch in it. If start detach throws an exception, we catch it and then we fall back to performing a synchronous close. But think about what we've done here. We're implementing a destructor that's going to be called over and over again for every file descriptor, and inside of it we have a dynamic allocation. We also have the possibility of an exception being thrown, and then in the second part of a talk called towards async everything, we have a fallback to a synchronous function. But maybe we imagine we're okay with all of this. Maybe cleanup is really so important we're willing to have this performance overhead. We're willing to dynamically allocate. We're willing to throw exceptions, and we're willing to perform synchronous syscalls. But what if I told you that start detached was removed from the standard library because it represented unstructured concurrency? And this may sound like the kind of thing that people who are too far in theory say to working programmers that should be discarded out of hand. After all, I have working programs to write. I don't have time to read your papers. I don't have time to RAIify your platonically ideal model of the world in my programs. I have a product that I need to ship. But what if I told you that unstructured concurrency isn't just a pejorative that people in the ivory tower throw around willy-nilly? What if I told you that saying something represents unstructured concurrency actually indicates that it is wrong? And I'm not just going to assert this, I'm going to walk you through a situation wherein this is borne out. Imagine that we have a fully running application. We come to the destructor of our file descriptor and we try to start detached. And this time our dynamic allocation succeeds. That operation is now detached exactly as the name suggests, which means that no one is tracking it. But in the last session, we talked about how we delegate an execution agent to run. We said that the external consumer injects intelligence about when they are done performing all operations, and that when they are done and signal that, we return to them and stop making forward progress. So imagine we start our close operation, which is so critical we're willing to throw away every principle of stood execution. We start that close operation, but it is detached. The high-level caller doesn't know that it exists. And so the high-level caller thinks that they are done with all their work. The high-level caller asks for the IOU ring context to stop running. Run returns and never makes forward progress ever again, leaving that close operation that was so critical, that we just reviewed must be driven through to completion, will never, ever complete. And what we're discovering is that destructors are fundamentally unworkable. What we're discovering is that we get to do the favorite activity of every single person who sits in Library Evolution Working Group, which is to implement in library features which reasonable people would say should be part of the language. And in doing this, we are in good company. Because as we talked about iteratively over the entire first session, stood execution is the library realization of the language concept of an asynchronous function. But we don't have to go this path alone. We can build on work that has been done by those before us. Because Kirk already took a first stab at solving this problem in P2849, introducing the idea of an async object, asynchronous constructors and destructors. And so we reach for his work and we start building on top of it. We reach for his work and we wonder, what would our file descriptor class look like if it was reified inside of Kirk's framework? And so we go through that rewrite. We see that our file class now has a nested object which has the API we previously associated with it. We have a layer above it which encapsulates only its construction and destruction semantics. But that raises the question of what goes inside of this wrapper. We've demoted our object to a nested type. How do we actually implement the rest of the functionality we require under Kirk's model? And since we're busy reinventing language features in library, we do that twice more, reinventing the language feature of a reference and the language feature of storage for an object. Then we turn around and we start using these. We provide an async construct function that accepts the storage it's going to construct the object into, thereby solving the problem of immovable types, and also accepts all of the arguments to use for that construction. And we see that it is fully curried, returning a sender which, if connected and started, has as a side effect the construction of an object in the storage. But construction and destruction are symmetric. If we have one, we must have the other, and so we go ahead and we add an async destructor. But this is not the end of the journey. I said this was our starting point, and we're going to iterate on top of the first stab that Kirk took at this problem. And so, like every good person who sits in Library Evolution Working Group, the first thing that I want to change about this protocol is, of course, the names. because it is my opinion that everything in std execution, or which interacts therewith, is presumptively async. That is the thrust of this paper. The thrust of this paper is we don't need to say async scope token for something in std execution. We can just say std execution scope token. And in the same vein, when we go back to our protocol, we can remove the async prefix from construct and destruct. They return senders, and so they are presumptively async. They don't need to be decorated therewith. But this is not the end of the degree of degeneracy you can achieve when you focus on bike shedding names. Because we already have library functionality that ends the lifetime of objects, except we don't call that functionality destruct, we instead call it destroy. And so returning to the protocol once more, we'll find that I have now updated yet another one of those names. But maybe we should take a step back and take stock of this entire protocol. Maybe we start asking ourselves important questions about why parts of it are required. Why do I need handle and storage? I said those were re-implementations of a language feature in library, but the language already has a perfectly good function for providing a reference. It's just a reference. And we saw in the last talk that senders and receivers can just send references because they are the asynchronous analog of a synchronous function, and synchronous functions can return a reference. And we don't need a library concept of storage for an object because the language already provides us with that, a sufficiently sized and aligned buffer of bytes. And so we imagine instead that we remove these. We remove these, and since we only have one nested type, we change its name to type. Then we see that construct and destruct have been updated, so they now accept a pointer to storage rather than a reference to a storage object which provides an indirection over that functionality. But now our protocol is looking kind of naked. The nakedness of it raises a question, which is why do we still have this nesting? Why is type a nested type? Why can't I bring it up to the top level? Realize the constructor as a static member function and the destructor as a regular member function. Rely on algorithms to mediate this protocol. And the reason for that is these arguments to the asynchronous constructor. Recall something I said all the way back at the beginning of the last session. I said that senders are not just the asynchronous analog of a synchronous function, but they are the asynchronous analog of a fully curried synchronous function. They do not await the binding of any further parameters. And one of the reasons for this that I gave is that it allows for separation of responsibilities. Someone can select a parameter but not be responsible for performing the invocation. This allows that now generic invocation to be performed elsewhere by someone else. But we see in this protocol that we are confusing two concerns. We are confusing two responsibilities. Because we are supposing that the same person who selects the constructor arguments is also selecting the position whereat the resulting object should be stored. What we're running into is the generic power that is brought to us by the currying of std execution. We are arriving at the principle that we should take this example and transitively and self-similarly apply it to our own protocol. That selecting the arguments to a constructor should not require us to select the storage in which that object will be constructed. And this was actually part of Kirk's original proposal. Kirk's original proposal not only admits async constructors with trailing arguments, but also provides utilities to iteratively bind those arguments until you obtain an async object whose construct function is unary, which awaits only the selection of the storage. But while that is a workable model, it is not self-similar with the model of senders and receivers. We do not have partially bound senders, we just have senders which are fully bound bits of latent execution. And so we return to our protocol and we RAIify this. We separate the responsibility for selecting the storage from the responsibility for selecting the arguments. When we construct that outer layer, thereby justifying it, we only select the arguments to be used to construct an object. Only later when someone calls construct do they iteratively select the next parameter in the cascading chain. But there's a problem here as well. The problem is that both of these member functions are const qualified. And now we have explicitly surfaced the fact that these objects have state. They have state that we could optimize based on the CV and ref qualification of. And there is a self-similarity argument with senders here as well, because senders can be differentially connectable depending on their CV and ref qualification. If you connect a sender which has curried arguments as an R value, it is more than welcome to move those arguments out of itself into the operation state. And maybe this is not a compelling argument in this context because everything that we are currying is a scalar. But there's no reason that has to be the case. There's no reason I can't choose that my interface is to provide the path as a stood string. Now my async object, my fully curried constructor, contains an object which is expensive to copy. If I then have to form a sender therefrom from an R-value async object, do I really want to pessimize and cause a copy anyway? And so instead what we do is we simply allow construct and destroy to be invoked on objects with any CD and ref qualification to benefit from this optimization. But in our cascade of solutions begetting problems, we haven't reached the end, because this raises an important question that is reified in this example. We curry all the arguments into a file, we obtain sufficiently sized and aligned storage, and then we go and obtain a pointer to that storage. Then we move F because we know we only want to construct one object therewith, and we obtain a sender. We imagine that we go off and we use it in some way. We construct that object, we use it, and now we are done with it. But being done with it requires us to go and interact with F again to obtain the destructor sender. It requires us each and every time we interact with an async object as an R value to commit the sin of a use after move. And we can solve this problem in turn. We can solve this problem in turn by simply going to our destroy function and making it static, saying that the only state it can depend on is the object that is resident in the storage to which that pointer points. But this raises an interesting and disturbing problem. An interesting and disturbing problem of API design. Because I said to you that destroy can go ahead and extract any parameterization it needs from the object in the storage to which that pointer points. But what part of this API design mandates that? What part of this API design mandates that you only call destroy with pointers pointing to live objects? The destroy function is always available. I can always call it, and nothing about that call enforces the fact that the storage that pointer points to actually contains an object within its lifetime. But also this formulation is taking and it is reifying something about our use of regular objects which is disturbing. And that is that a lot of our use of objects is basically an abuse of the C++ object model. We make use of objects not for their objectness, but for some other purpose. And let's explore both of these arguments together in an example. I have some function f which I want to invoke under a critical section. And so I create a mutex, and then inside of an anonymous scope, I construct a lockguard. I construct a lockguard, and inside the constructor of that lockguard, it acquires the mutex. It acquires the mutex, and as a result of that construction, it creates an object. But I don't really care about the objectness of L. I don't care about its storage. I don't care about its address. I don't care about its identity. It is simply an abuse of functionality which allows me to instrument the exit from the scope to perform the symmetric action to that which would perform on the entrance there too. But think further on the API that we're seeing here. Think further on what this means. When I call the constructor of L, I pass it M and it acquires the lock. And as a side effect of the constructor running, the object comes into being. It becomes possible now to destroy that object, something that was not previously possible because the object to destroy did not exist. We are seeing that API principle borne out in the design of regular synchronous objects, which was not borne out on the preceding slide. You can't call the destructor easily on an object which does not exist. And so let's think about how we can reformulate this. Let's think about how we can reformulate this in a way that does not abuse the objectness of objects, but which still reifies that design principle that we should make it difficult or impossible to do invalid things. We take, and instead of having an object, we have a higher order function. This higher order function accepts the mutex and then locks it. But in addition to locking it, it returns to us a new function. The new function, if invoked, undoes whatever it is that enter scopes did. When you call enter scope, you not only do something, but you uncover from an API design point of view the symmetric action which must be performed to undo it in a manner which cannot easily be accessed without doing the needful interaction with the protocol. As we look down below, we see this actually borne out in the use. We call enter scope and we obtain an exit scope object. We perform the actions in the critical section, and then we call exit scope to symmetrically undo whatever it is that entering that scope did. Ignore for a moment this is exception unsafe. Layering exception safety on top of things like this is easy when you write a generic algorithm. Think about what we've done in walking through this example, though. We entered this slide using objects. in some sense, abusing them. And we don't have access to constructors and destructors and therefore objects in the asynchronous domain. But then we took the same thing and we reified it as a higher order function. But senders and receivers are just the asynchronous realization of regular synchronous functions. And so if we can write this symmetric action, which establishes invariance over a scope and yields to us the symmetric action which must be performed to undo it as a regular function, then it stands to reason that we can do it as a sender too. We can rewrite exit enter scope as the same moral operation except reified instead of as a higher order function, as instead a higher order sender. When we call enter scope with the mutex, we now return a sender. A sender which, if it was ever connected and started, would have the effect of acquiring the mutex. But it doesn't just acquire the mutex, it also yields to us another sender. It is, as I just said, a higher order sender. This sender, if ever connected and started, undoes the actions that were performed by the first one, symmetrically resets the state of the world to exactly the state it was in before we went down this pathway. And so what we're discovering is that enter scope doesn't just return a sender. We're uncovering a generic taxonomy that exists on top of senders, because exit scope returns instead an enter scope sender. And that means that that inner then returns an exit scope sender. We have uncovered a generic language lurking inside of this. It is this generic language that is the central thrust of my paper, which aims to succeed P2849. The realization that this kind of management can be reified as scopes all the way down. The thrust of P3955. But the point of this paper is not just a realization. The point of this paper is to establish a generic language we can use to interact with these concepts asynchronously. And so we set out on that journey. We set out modeling the actual generic language of enter and exit scope senders by defining the concepts which identify them. An exit scope sender satisfies the exit scope sender concept if and only if it is a sender and if it can be decay copied and moved without throwing an exception. We see that principle we uncovered earlier in the talk, that cleanup can't fail at any level of analysis, reified in this concept. But notice what this concept is missing. It's missing anything about the asynchronous part of that operation. Does connect throw exceptions? Can it send an error completion signature? And the reason for this is because these determinations are fundamentally impossible to make in std execution without another argument, without the environment in which that asynchronous operation will run. What we are discovering is that we need not just a unary concept, but also a binary one. We need exit scope sender in symmetrically with how the standard provides both sender and sender in. And so we see that exit scope sender in subsumes exit scope sender and also subsumes std execution sender in. And then we see that we're establishing properties of the asynchronous part of the sender. It must not throw exceptions when it is connected in that environment. And its asynchronous part must always complete successfully and send exactly 0 parameters. But the tail of this concept definition is interesting. It warrants further attention. Because as P2300 was adopted into the standard in St. Louis, the authoring of this is no-throw connectable in-V type trait was impossible. It was impossible to determine whether or not a sender threw an exception when connected in an environment. Instead, you needed a concrete receiver to make that determination. But this inhibited exactly the kinds of computations we see on this slide. And so I wrote a paper to address that. This paper was adopted into C++26, but it just makes a change to the framework that makes this determination possible. It doesn't actually surface any interface that actually provides users with a turnkey way to make that determination. But there's always going to be another C++ standard. There was C++26 and there will be C++29. And so I have authored a paper for the C++29 timeframe that proposes that we adopt exactly this type trait, that we make it easy for users to perform this computation, which we unlocked the ability to compute in C++26. And so on my preceding slide, I am just supposing this paper has already been adopted, that we already have access to this type trait. Rest easy knowing that you can author it. It's just a little bit complicated to do so. But there's also something else interesting in this concept. The way in which I check the completion signatures. It's just too convenient. Because we've seen that the way we encapsulate completion signatures is by instantiating std execution completion signatures, with a function type representing each of the completion signatures. Recall earlier when we were talking about std execution, then gaining an additional completion, we saw an additional function type appear in the parameter list, which was used to instantiate std execution completion signatures. But notably, we saw that error signature appear after the value signature. Nothing in std execution says this has to be the case. Std execution doesn't mandate these completion signatures to be provided in any particular order. The reason I'm able to very easily make the determination here is because I've just abused the fact that you can't reorder one element. It has a single canonical ordering, and so I can use isSameV. But this isn't a very satisfying answer. It's not a very satisfying answer to say that I get to cheat in my presentation, but if you want to make this determination yourself, in the general case, you should go ahead and write a lot of complicated template metaprogramming that very few people can get right. But this is a talk about std execution. Std execution is a C++26 feature. This is a C++26 talk. We don't have to write complicated, impossible to understand metaprogramming anymore. Instead, we can just call a const eval reflection function. We can ask if these are the same completion signatures and pass a reflection of the completion signatures we want to compare. We can go and we can very easily implement this. We take in the two meta infos, and then we need to define a predicate, a way that we can order them to ensure that they are canonical. And thanks to Gaspar, who's sitting in the front row, this is actually possible because we have type order, which allows us to establish a single ordering over types, which is projected into our metaprogramming universe via the type order function. And so we define this predicate we can use to order the signatures. Recall the signatures are the template arguments provided to instantiate std execution completion signatures. The arguments to this function are both reflections of such an instantiation. And so we just go ahead and we extract the template arguments from both of them, extract them as a vector at const eval time, use a regular algorithm to sort them. And then of course at the very end we use vectors equals equals operator to see if we actually have the same set of completion signatures. But this just brings us to the end of determining whether or not something is an exit scope sender. Now we need to determine whether or not something is an enter scope sender, but recall our formulation. An enter scope sender completes its associated asynchronous operation by sending us another sender, by sending us an exit scope sender. And so it would be really nice if we had a type alias that allows us to take an enter scope sender and extract its exit scope sender type. But once again, we're getting into computations over completion signatures, the kinds of computations that are very annoying to implement in C++23. Fortunate it is then that this is not a C++23 talk, and we can just write some reflection to solve this problem. We can write a const eval meta function which computes the exit scope sender of a certain sender. The function accepts a reflection of the sender type and a reflection of the environment in which it will be connected. Now we define a helper, getSender, which accepts the reflection of a completion. Recall that a completion is a function type. It has a return type that gives the channel it's sent on and parameters that give all of the arguments. And so we extract the parameters and we verify there is exactly one of them, because we are looking for a signature that sends exactly one argument, which is an exit scope sender. Having verified there's exactly one argument, we simply return the front argument. We hope that it's a sender. We'll verify that later. Which brings us to another helper, isSender completion, which gets the reflection of a completion once more and verifies that it sends an exit scope sender. We start by making sure that it's a value completion. If it's an error or stopped completion, that's fine, and we ignore it. Entering a scope can fail. It's exiting a scope that must run through to completion. Then we go ahead and we grab that sender. We call getSender to get back a reflection of the sender type, and we substitute into the exit scope sender in concept both of those arguments. This obtains a Boolean, but we don't know that yet because all we get back is a std meta info, which is a reflection of that Boolean, and so we extract a Boolean from that meta info and check to see if the concept is satisfied. If it is, we return true. Otherwise, we throw an exception because we can't compute the exit scope sender. Which brings us to actually implementing this on top of our sender and our environment. We get out the template arguments of the instantiation of std execution completion signatures, but where does that come from? That comes, of course, from substituting into completion signatures of T both the sender and the environment. With this collection in hand, we then need to scan over it and see if there are any sender completions. If there are not, we throw an exception. Otherwise, we verify that there is only a unique such completion because we mandate that enter scope senders only send an exit scope sender in one single way. Ruslan.
And those are const expressions, right?
Yeah, this will check that they are constant expressions. There's actually, the next slide is going to splice this in. And then after that, we're going to rely on a type name query on that. I've been assured very vigorously by the P2996 officers that's supposed to actually evaluate defaults when a compile time exception is thrown, but GCC 16.1 disagrees. So yeah, it's unfortunate. But yeah, it'll verify these are constant expressions, and if they throw exceptions at compile time, they will result in some form of diagnostic. It might be better to use get completion signatures, but I haven't gotten used to using that API since Eric added it. And in std.exec, particularly, it doesn't offer that much value because std.exec is a 20 library, and so it doesn't have the compile time exceptions. This code actually does work. I put it into Compiler Explorer and used GCC trunk to ensure that it works, except what I just talked about. But yeah, I'm just not in the habit of using the functional version. For those of you who don't keep up, completion signatures of T just goes out to a const eval function called get completion signatures, which allows you to be directly in line of the compile time exceptions. That throws when it can't compute the completion signatures. So with this const eval function implemented, we actually turn our attention back to implementing exit scope sender of T. And we do this by simply splicing in the std meta info that is returned thereby. Which brings us to establishing our generic language over enter scope senders. But we realize as we think about it that absent an environment, we can't actually establish any useful properties for an enter scope sender. All we can do is check that it is a sender and leave further checks until we have available an environment. But once we do have an environment, not only do we subsume exit scope sender, not only do we subsume sender in, but we can also require that we can compute the exit scope sender of that type. If we can't compute it, then it can't be an enter scope sender because it either sends multiple exit scope senders or sends no exit scope senders or sends something that isn't an exit scope sender at all. But the whole point of defining concepts is not just to define concepts, it's to enable algorithms to operate on top of those concepts. So now we're left discovering the algorithmic language of enter and scope senders. The basis operation is an operation called within, which accepts an exit scope sender and a regular sender. The way this asynchronous operation works is it uses the exit scope sender to the enter scope sender to establish whatever invariants are associated therewith. Out the other end, it of course receives an exit scope sender, but it simply stores this for now. Then it goes ahead and starts the asynchronous operation as the result of connecting the second sender. It runs that asynchronous operation within the scope formed by the enter scope sender. When that operation completes, it stores the completion thereof, connects the exit scope sender, and allows it to run to completion symmetrically, undoing whatever invariants were established in entering the scope. Here we see that exception safety problem I highlighted earlier, mediated dutifully by an algorithm. But this algorithm only accepts a single enter scope sender. What if we want many invariants that we want to satisfy? And so we can enrich our ecosystem with still further algorithms. An algorithm called enter scopes, which accepts a variadic pack of enter scope senders. It combines them together into a single enter scope sender, which works as follows. When it is connected and started, it starts the asynchronous operations of every single child enter scope sender at the same time. If it ever becomes aware that any of its children send anything but a value completion, it requests that all of the remainder of its children stop as well. Then it fails to enter the scope. But if the scope is entered, if all those invariants are established, it sends an exit scope sender that of course will undo the entrance of all of those scopes in parallel. Of course, if it encounters any errors when it is entering the scope, it is going to undo the side effects of every enter scope sender that succeeded before it sends a failure. It is going to abstract away all of the exception safety problems the language takes care of for us in the synchronous domain into the asynchronous one. But this process of establishing invariants in parallel, of running all these operations that establish the invariants for a scope in parallel, is alien to people who write regular synchronous programs. We establish these invariants in a very particular order and unwind them in the opposite order. But we could just add another algorithm that does that. We add one called nest scopes, which also accepts a variadic pack of enter scope senders and returns an enter scope sender. An enter scope sender which, if connected and started, enters each of those scopes in sequence. If any of those fail, it undoes the actions of all the ones that have succeeded and sends an error. Otherwise, it sends an exit scope sender that undoes all of those actions in reverse order, in the order that regular C++ programmers expect by analogy with the regular synchronous domain. But as we return from this exploration of algorithms to our example, we realize something. We realize that we just hyperfixated on this lock guard. something which in some sense constitutes an abuse of the C++ object model. But there's something else on the slide that we haven't addressed yet. There is a bona fide object which does occupy meaningful storage, whose identity we do care about, whose member functions we do want to call, which we are not simply abusing to instrument the rising and falling edges of entering and exiting a scope. But then we think about something. We think about the reason why we're able to abuse objects to achieve the purpose of a scope guard. And that is because C++ objects are constructed and then destroyed on the exit from the scope. Construction and destruction of a regular C++ object is just a side effect established when entering a scope and one that is torn down when exiting, except it is the special case where the establishment of the invariant is the construction of an object in some storage, where the undoing of that action is the destruction thereof. And so we can return to our higher order synchronous function example, except this time it has exactly those side effects. A construct function which accepts a pointer to storage now instead of a mutex, because it is going to construct that mutex rather than locking it, which constructs a mutex in that storage and returns an exit scope action which goes to that storage and destroys the object. Then we prepare an appropriately sized and aligned buffer of bytes. We obtain a pointer to the storage and we call construct therewith. This not only constructs our mutex, but returns us an action we can perform to destroy it. Then we're more than welcome to go and acquire a reference to the newly constructed object and use it as usual. Use it as usual, and then when we are done with it, call destroy. Except that in this formulation, I'm taking advantage of a special property we have here. A special property which is that mutex has a default constructor I want to use. There are no parameters to be selected. What if instead I wanted to use this model to construct a string which has some non-empty value? For example, hello world. And here when we run into that currying argument that we discussed at length earlier, when we were reviewing Kirk's ecosystem. We now just need to add another level of abstraction, another level of parameter binding so we can fully separate concerns and also allow for construction and destruction of objects. And so I provide a construct function that is doubly a higher order function. It accepts the arguments to the constructor and returns a new function which awaits only the selection of storage, away from whom the responsibility of selecting constructor arguments has been abstracted. Then we go and we construct into that storage and return in turn another function which will destroy it. And we can see this borne out towards the bottom of the slide. We first select the constructor arguments, and then we go and we take that curried function and we select the storage. It returns to us the destroy action. We can use the stood string, and then at the end of that protocol, destroy it.
Why do we need longer there?
So the pointer to the storage doesn't point to an object. So I create an object in that storage, but I need to obtain a pointer to the object, not to the storage.
But haven't I implicitly created the lifetime of the thing by constructing it, and therefore I know that there's a thing there and I can cast it?
Stood string is not an implicit lifetime type.
Sorry.
And even if it is an implicit lifetime type, reinterpret cast from a buffer of bytes does not implicitly start lifetimes. You need to do something like operator, like placement new, mem move, mem copy, any of those good things. So what happens is inside, you can see that very carefully inside of construct, I get a pointer back from construct at, which points to the object, and then I take and capture that pointer, not the storage pointer, and use it for destroy at. That pointer points to an object, but on the outside, because the interface surface is consistent, I just get back an invocable, which means I need to use launder to tell the compiler there's actually an object in that storage now, and if there's not, there's undefined behavior. Whereas if I just did the dereference of the storage pointer, that would probably work on every implementation, but it would be undefined behavior as far as I understand. So now we need to take this ecosystem and project it finally into the asynchronous domain. Repeat that transformation wherein we take a regular function and we realize it as a sender. And to do this by example, I'm going to walk through something that's proposed by P3955, the sync object wrapper, which takes a regular synchronous function and makes it an asynchronously constructible asynchronous object. The first thing we see in its interface is that it reveals the type of object it constructs, so an algorithm can extract this and use this information. We know that our ecosystem admits only fully curried constructors, and so we see that currying. We select the arguments and we store them in a tuple. Then we get to the truly interesting part of the model. We get to the part of the model where we need to then enter scope sender. We need to asynchronously construct and destroy this object. And so we dive right into the implementation thereof. We return a sender which lazily lifts this construction, which uses placement new and make from tuple in order to perform the construction. But that's not the end of the responsibilities of an enter scope sender. We just had a side effect. We just established an invariant that there is an object within its lifetime in the storage which was bound into our sender. And so it is incumbent upon us, if we want to be an enter scope sender, to yield an action which undoes that, to yield another sender which has as a side effect the destruction of the object in that storage. But this is another concept. This is another generic language we need to define concepts and algorithms on top of in order to be able to use it. And so we start with some helper type aliases. We want to be able to extract that type argument so we can inspect an async object and figure out exactly what type it actually constructs. Then, of course, we need to figure out what kind of enter scope sender it yields, and so we have a type trait for that as well. Now we need to figure out what it means to be an async object, to define the concept, therefore. We require decay copyability and movability. We require that whatever it constructs is an object type, and we also require that whatever it yields from its function call operator with appropriate storage is an enter scope sender. But recall how shallow that determination is. Enter scope sender without an environment only checks that that enter scope sender is a sender. It doesn't check any of the interesting properties thereof. And so we need another concept, a binary one called object in, which subsumes object and performs the enter scope sender in check in order to establish this thing is actually an enter scope sender with all of the attendant requirements thereof. But this is just the concepts. Concepts exist in order to constrain algorithms. Let's see the algorithmic surface of these concepts. The algorithm called lifetime, one which accepts and enter scopes a factory and a pack of objects. And so we need to unpack all of this. The pack of objects is clear in its purpose. These are fully curried asynchronous constructors that our algorithm has to figure out how to mediate, how to provide the correct storage, how to start their lifetimes correctly, how to give us references to them, and then when we're done, destroy all of them. But we know that part of our object protocol is obtaining enter scope senders. And so we can imagine that lifetime can take and project those objects into enter scope senders once it has established appropriate storage. The sender that it returns can be connected to form an operation state. That operation state can contain in situ sufficiently aligned and sized buffers of bytes to hold all of those objects. To form storage for all of those objects, we can then provide to the async objects to obtain enter scope senders. But note the plural there, enter scope senders. Our basis operation for entering scopes and performing some algorithm inside of that scope accepts a single sender. And so we need some way to combine all of these scopes together. But as we saw in the algorithmic language of enter scope senders, there are multiple ways to do that. And so enter scopes allows for you to generically select the means by which that is accomplished. Allows you to generically select the means by which the enter scope senders of all of the objects will be combined to pick between, for example, enter scopes and nest scopes. But that leaves the factory. That leaves the purpose of the factory unclear. But think about what we're doing. We're going to asynchronously construct a bunch of objects in some storage. We're then going to obtain references to those objects and do what? We need some factory that gives us asynchronous execution which accepts those references and uses them for some asynchronous task. We need a factory function which, much like letValue, accepts a pack of references and yields back to us a sender. A sender which represents the asynchronous execution that should be performed while all of those operations are within their now asynchronous lifetimes. But we can make a simpler version of lifetime. We can simply fix one of those decisions we ask our users to make. We can provide a version that simply fixes the strategy by which those enter scope senders will be combined. By supposing that you always want to enter the scopes in parallel. You want to construct all of your objects at the same time and destroy them equally. And this is not just the exploration of a paper. This is not just the exploration of an idea that I had. I've actually implemented this and I have an open PR against NVIDIA StudExec. So you can go ahead and you can download that PR and you can play with enter and exit scope senders today. But think about how we started this talk. We started this talk picking up on the first session, picking up on that file descriptor wrapper, staring at those glibc functions that we wanted to render asynchronous. And so maybe we should close the loop on that. Maybe we should go back to our file descriptor wrapper and finally realize it as a fully featured async object, one that has no synchronous parts. And so we see the interface that we're used to for an async object by this time. We have a constructor which curries all the arguments. We have a nested type which has the interface that we built for our file descriptor wrapper in the first session. And then of course we have private member variables for all of the curried arguments. But the interesting part of an async object is that function call operator, which yields an enter scope sender that is going to construct those objects asynchronously and then provide an exit scope sender which destroys them. And so now we're going to look at the implementation thereof. The function call operator which accepts the needful storage and returns a sender, the asynchronous analog after all of this time of a constructor. But we know what we're going to find therein. We spent the entire first session obsessing over asynchronous syscalls made via IOU ring. And we know that our file descriptor wrapper is just a wrapper around open@. We already know how to stamp that out. We saw that earlier in the talk. But then when that operation completes, when it completes and gives us a CQE, we have to glue this into our async object and enter scope sender ecosystem. We have to go and we have to handle errors appropriately, throwing an exception if we fail to acquire the needful resources from the kernel. Then we go and we construct that shell of an object. We construct that shell of an object and we give it that file descriptor we just obtained from the kernel. That completes the establishments of the invariants which hold in this scope. But that's not the only purpose of an enter scope sender. It doesn't just establish invariants, it also gives us a pathway to undo them. And so we return a sender which performs another asynchronous syscall, which goes and asynchronously closes the file descriptor that we opened earlier. And thereafter, once that syscall completes, goes and destroys the shell of a C++ object which surrounds it. But this is just an async object which opens and closes file descriptors, which asynchronously reads from them. The sort of thing that is very interesting to people who are obsessed with writing libraries but not very interested in using them. And so let's take this library functionality we built and do something. Let's write an actual C++ application which is asynchronous. Let's take a simple example. Let's write a very simple asynchronous cat, which simply goes and writes a file to standard out. But first, before we leave this slide, let's make sure we add unstoppable to ensure that we don't cancel closing this file descriptor. Because as we compose this on subsequent slides into an application, we expose the possibility that stop tokens will be provided all the way through from the highest level. The person requesting a stop may not know there are resources left to be disposed of, and so its stop, if we didn't wrap in unstoppable, might have the side effect of canceling that close. Which brings us to our async cat, which brings us to a function which returns a sender, which accepts an IOU ring context and a file path. And inside of this function, we know what we need to do. We know we need to construct a file descriptor that is a handle to that path, and we know we have to do it asynchronously. And so we reach for our lifetime algorithm. We see it now in actual use. We see the currying of the constructor arguments there at the bottom of the slide, but we also see that we create several other objects we want to have access to inside of the asynchronous scope we are about to enter. We want a borrowed file descriptor which has our context and is a handler to standard out, and we also want a vector of bytes that we can use throughout our operation to read into and write from. And in accordance with our formulation of lifetime, we see at the top there that we accept reference parameters that correspond to those fully curried constructors. We're going to return a sender from this function, and throughout its asynchronous lifetime, we are going to have access to a file type. We'll have access to a borrowed file descriptor, and we'll have access to a vector. The fact that these are references doesn't matter. They are references into an operation state which structured concurrency dictates outlives us. We can rely on them without fear of dangling. Which brings us to actually writing the needful code. Writing, once again, an asynchronous loop. We use that read some basis operation that we spent the last 2 sessions bootstrapping and also supporting. And then we capture the number of bytes we've read. But reading isn't the only point of cat. We need to go and we need to write those bytes back. And so we write to our output the same buffer of bytes. And once that write completes, if the last read indicated end of file, we return true, causing our asynchronous loop to break. But once again, as is becoming thematic of this talk, we have additional questions. I said this would be an application, but it's just a function. We need some main that calls it. And so we go and we do that. We go and we implement that, and we see all of the detritus that we normally write when we bootstrap main being filled in. We check the command line arguments, we catch all the exceptions, we write to standard error when one of them gets thrown in, and we exit with exit failure. But now we're tasked with entering an asynchronous domain, taking this fundamentally synchronous main and reifying it asynchronously. And the way we're going to do that is by synchronously waiting for our asynchronous operation to complete. But our asynchronous operation needs an IOU ring context. It doesn't just need an IOU ring context, it also needs that IOU ring context combined with assurances that forward progress will be made thereupon as is needed. And so we are going to mediate that with an algorithm called run on polled IOU ring, which brings us back to the beginning of the talk, where I laid out those bullets of what we hope to achieve and pointed out that with submission queue polling, we don't need to make any syscalls to interact with IOU ring. This asynchronous algorithm creates an IOU ring context and invokes this factory function we're about to fill in. Then the sender return thereby is connected and started, and run is called on the IOU ring context until that nested operation reports completion. And of course, we know the asynchronous operation we're going to select. We know the application we're trying to write. We simply return the sender form by calling cat with the context and a path. But half the fun of writing an application is actually running it, actually seeing what it does when you compile it and let it loose. And so let's see if we can get our async cat to print hello world. And verily we see that it does so. But our application's completing successfully is in some sense the least interesting way an application can complete. Far more interesting is the complexities of getting it to complete in a sane way when it fails. And so we say, what would happen if I went and I read from a file that doesn't exist? And the application doesn't crash or hang. The application returns a non-zero exit code and prints out that there was no such file or directory. But what if we do something more complicated? Explore a less common failure modality. What if we try to write to a file descriptor that is a handle to a file system that is always full? Well, in that case, we get the same graceful failure. A graceful failure that identifies the asynchronous syscall and says there was no space left on device. But think about that curveball I just threw you at the last moment. I mentioned in a bullet earlier in this talk that we could have submission queue polling. And in the last minute I said, I'm going to use this algorithm that gets us submission queue polling, allows us to submit asynchronous syscalls to the Linux kernel without using the synchronous syscall protocol at all. And so let's do something more challenging. Let's run that successful case under strace. Let's see whether or not I'm lying to you. And of course, when you strace any program, it spits out a bunch of junk that you're not interested in. And so we're just going to throw that away. And of course, we need to go and ask the kernel to give us an IOU ring, and we see all of those syscalls being made. We call IOU ring setup and then mmap exactly as I said at the beginning of the last session. And we know from last session that our IOU ring context has an event FD, and so we see that being allocated. Then we use brk in order to get space for that vector we saw just a few slides ago, and we use IOU ring enter to wake up the submission queue polling thread so that it's ready to pull things out of the submission ring. But then something interesting happens. We stop seeing output from strace. We don't see us telling us about any more syscalls. We just see hello world. And after hello world has been printed, the application, of course, doesn't call exit, doesn't call abort, it doesn't crash or hang. It just runs all of the needful destructors and exits. We've gone and we've bootstrapped an asynchronous ecosystem which can run with 0 syscalls and 0 allocations. And so as we leave this talk, we ask ourselves, what have we done over the last 2 sessions? What are we walking away with? We spent the entire first session bootstrapping an IOU ring context, and at the end of that session, I told you that was not the interesting thing we had done. What we had discovered is that in our traversal of every layer of abstraction, senders were a perfect fit for every single one of them. And then in this talk, we realized that we could model scope entrance and exit as calls to regular functions, albeit higher order ones. But that was not the interesting thing we discovered, because we have the asynchronous analog of regular functions, and so we discovered that we can model such entrance of scopes and clean up on the exit thereof as senders. And then we had the realization that construction and destruction are just actions performed entering and exiting a scope with the additional enrichment of storage. It's a particular class of side effect that can occur as entrance into a scope. But that wasn't the fundamental realization there either, because what that allowed us to do was project an entire asynchronous ecosystem which provides all of the functionality of regular synchronous constructors and destructors. And so maybe as this talk comes to an end, the question we ask shouldn't be, what have we done? Instead, it should be, what is left? Because if we visited the abstraction hierarchy at every level of analysis, and at every single one of them we discovered a sender, and then we looked at regular synchronous functions, we looked at constructors and destructors, and we found senders there too. Can it be truly said that anything remains between us and async everything? Vito and then Ruslan.
So it's interesting you talked about detached and its history as being removed because it was unstructured concurrency. But we replaced it with counting scope, which kind of does a very different thing than you were discussing here when you're discussing scopes. So is this I guess the nature of the question is, like, do you envision these constructor-destructor scopes as fundamentally different than counting scope and its position in the standard?
Yeah, so there's a really interesting thread of discussion, which, I mean, I don't know. I pieced it together by talking to people, and the idea behind it is basically that scope was a bad name for counting scope.
Okay.
The issue is that I think a lot of the other names that people use for this concept are also like kind of not great. One of the Python structured concurrency libraries uses nursery.
Yes, yeah, because it contains trees.
Yeah, right. And so we used scope as a name for that. And in my development of this concept, the reason I called it scope was because I realized I basically took Kirk's proposal and implemented it, and then changed it and implemented that, and then changed it and implemented that. And then I got to a point where I was trying to take Kirk's model and make it support construct and destruct that didn't take storage to do the scope guard thing. And then it also took storage. And the generic programming required to support both those models everywhere was awful, right? It was the kind of awful metaprogramming that you get when you try and write a synchronous when all, right? Because a synchronous when all takes regular functions, but regular functions don't have obligatory early binding of parameters. And so you're like, okay, which of these are functions, which of these are parameters that I have to apply into it? That kind of generic programming at scale. And so then I realized, okay, well, these are just, what I actually want the basis operation is like what we think of as a scope guard, right? So scope. And then you can make construction and destruction on top of that. And so I have no expectation that these names are going to get through Lug without being changed. Okay. I feel like anyone who expects their names to get through Lug without being changed is setting themselves up for disappointment.
They will not.
And to answer your original question, there's two things. I'm going to answer your question and tell you something interesting. So I don't think this is related at all to the functionality that the counting scope provides. But what's interesting about it is that a huge discussion that's gone on both in the room in Lug and also like offline is how do you safely use scopes, right? Because scopes have this weird biphasic teardown, right? Where you have to run an asynchronous operation to like join the scope, and then you destroy the actual C++ object shell that's left behind. And so one of the things you can immediately do with everything that I talked about in this talk is you can write a real counting scope that doesn't have this footgut, right? Where it has it has an asynchronous operation you need like pinky promise you're going to run before it goes away. Otherwise, you have like weird undefined behavior, and you break all the promises that we build the structured concurrency of stood execution on top of. Ruslan.
So, first of all, I want to get back to Mark's question, because unless I'm missing something, I'm not sure that you really need this did longer. But I don't want to discuss it now. We probably will find some time to discuss it offline, because I'm pretty sure everybody is eager to this HRT sponsor event.
Well, so with the launder thing, I'm reasonably sure that you do need it. The instance in which you wouldn't need it, which is in my understanding, right? Like if someone in core tells me I'm wrong, then I'm just wrong, right? That's all there is to it. My understanding is that, interesting, like in the string example, right? If that pointer pointed to a string, and then you provided that pointer to a string as storage, which would create a new string on top of the old string, right? And never run the strings destructor, right? Which is well defined for some reason. Then you wouldn't need launder, because strings are transparently replaceable with each other. And so the pointer to the old one will become a pointer to the new one. But because it's pointer to storage, right? Going from storage to object in the storage requires launder, I believe. I think that's the whole reason the launder exists.
Again, maybe I missed that in your talk, but yeah, like we will discuss it later. And another point is like another question that I want to ask, and you don't need to answer it actually. So you said that everything in std execution is asynchronous. How do you feel about std execution part?
Oh,
is
well,
better. I said you don't need to answer it.
Steve.
Yeah, no, I was just going to say that I think you're right because although I've not worked with them, cherry architectures, which do the type tagging of memory, that's the one that gets violated that Launder helps fix.
You should
Because
put a
it's
black
like
box of
you've got a
Launder,
pointer
right?
to storage and a pointer to string at the same place. In some architectures, those just aren't the same pointer.
You put stood Launder on a slide in a room full of C++ experts. You completely derailed.
So, hey, we need somebody to fill the rest of the time with questions. Gasper and then Mark.
Yeah, so I'm wondering why you needed both lifetime and enter scope, was it?
The fundamental algorithm of enter scopes is within.
Right. I mean, in Python, that's basically called width, right?
I call async with, yes.
Yeah.
Yeah.
And those async senders that you're pushing in there are yielding something effectively at the end, right?
Yeah,
they're yielding their async destructor
Yes,
function.
exactly, yeah.
But you also have a side channel
Yes,
for the objects.
yes.
Do we need two algorithms, or can we just figure out this one yields something from its side channel and this one doesn't?
It is possible that you could rewrite within to support enter scope, like that you could reformulate the entire generic, like, you know, calculus of enter scope senders, so that enter scope senders have to have exactly, maybe they're not even exactly one value completion, but maybe they'd have like a homogeneous exit scope sender type, and then they can send n things after that. And like then you get back to Kirk's model, because one of the things in Kirk's model that's talked about in the slides, but never said, is that in Kirk's model, construct sent the reference, so you didn't need the launder. Right? The reason lifetime is required is because if you are strict about what enter scope senders can yield, then you need to have the storage of the side channel, which means you don't get the like blessed core language pointer to the object, so you use launder to get it out the other side, and that's what lifetime does. Lifetime, in my implementation, I think lifetime is just like a scaffolding that surrounds one call to within, right? And the scaffolding is like, here's storage, and I call the function call operator of all the objects. Mark?
Yeah. So thank you. It looks like so with coroutines there was a language feature, and then we as a committee stitched it together to a library feature, std execution, and now they're together. It feels like what you're designing in the second talk is a library feature that could become a language feature.
It's possible. It would probably be surfaced by like async with in Python, but in C++ somehow. And the problem is that the language, the vocabulary we have for speaking about asynchronous operations in the language is coroutines. And an enter scope sender that's a coroutine is totally fine, right? Like it has performance pessimizations, but structurally from like this platonic domain, it's fine. Enter scope senders are a completely different matter. Right, because exit scope senders are a completely different matter, because exit scope senders have this strict requirement that they must complete with exactly set value, and that's something that coroutines can never give you, right? Because they always have frame allocation failure.
Oh, I see. Yeah, thank you.
Steve, and then was Michael up before?
I think Mike.
Michael then. Sorry.
Back when the start attached, it seems to me that the problem is that the one that was inside of P2300 was returning void.
Yes.
And our implementation doesn't return void. It returns an optional a stop token, so that it is no longer unstructured concurrency. It's now structured. I can have complete control of the item. Now, was this discussed or?
But the problem with the stop token is a stop token lets you issue a stop request, which is non-binding and does not need to be satisfied on any time horizon.
Yeah, you'd have to return something that exposes you the completion and not the request for completion.
Yeah, so you need like the return of a sender, which when connected and started, requests stop and then waits for the completion.
You effectively need a future. You need to return a future.
Yeah, and so like that, the reason it was removed is because async scopes do this better, right? You like nest the sender inside an async scope, and in some sense it's detached because it's not attached to you, it's attached to the async scope. And then later on, when you want the work to fan in, you run join. But as I said before, you can mediate that with an async destructor.
Okay,
We don't have.
I'll have to take a
Our
look at that.
objects never die.
Yeah, our objects never die, so that's a different problem.
Yeah.
But
Right, like well, a lot of the corner cases you run into with unstructured concurrency, or like even the limit case of like slightly wrong things you can do in structured concurrency, are only exposed if you do pathological things. Like if you have a receiver whose set value completion immediately deletes the operation state. I actually have unit tests in several of my libraries that have a convenience wrapper to invent a receiver that has this relationship with its operation state. Because if you just plug these into random algorithms, you'll be surprised how many times ASAN is like, what are you doing? Right? You like called set value and then did something that touches the operation state, but like they could have destroyed it. If your objects never die, right, you don't have these concerns, right? That like structurally your entire program. Yeah.
They do die the operation states get destroyed. The storage never dies.
Oh, okay. Yeah. So the C++ object dies, but the storage does not die. Yeah. Steve?
Yeah, well, two things. It's like, one, I guess within, okay. You want to put that exit scope like at the end of your
Yes.
sender chain. So I guess within you're doing like some kind of let star, like doing the monadic bind around it.
Yeah, and so this is one of the places where I perhaps idiosyncratically very strongly disagree with the design of the way the standard library is written. Because the standard library for stood execution has two things that are problematic from my point of view. One, every time you want to do this operation, which I think of as like a pause and resume, right? Like, oh, your asynchronous operation running, pause, I need to like do something, right? Like finally in exec, not in stood exec extensions, finally is like this, right? Like it runs something when your operation completes, so it has to store the completions somewhere. And so the things that I don't like, and I had a side conversation after the last talk. One of the reasons that informed the API design of the IOU ring context was that I wanted to avoid using let value because let value is very badly behaved if you send it a reference. Because it decay copies everything.
Oh yeah.
Which is, I don't like that about all the algorithms in the standard library. If I declare I'm sending you a reference, I want you to save the reference and send I'll declare value if I want to send you one. The other problem the standard library has that I'm hoping we can fix, I don't see any of the implementers availing themselves of it, and I don't see anyone writing algorithms doing this in a sane way, is that there's blanket language in the exec clause that says that completion signatures that declare an R value qualified completion are the same as a PR value completion, which I think is pathological, right? Like if my operation says it sends you an R value reference, it sends you an R value reference, not a PR value, and so when you store and resume it, you better do the reference. So that within, to answer your question, does the store, but it does the store with a helper that I've written which respects L value referenceness and R value referenceness.
Okay.
Yeah.
The other thing is that I'm glad you did this talk rather than me, but this fits in with sender. The whole sender model is a full model of computer languages.
Yes.
So of course we can redo scopes and constructors and destructors. You just have to start up from the beginning
You
again.
get to start off from the bottom, and notably, unlike coroutines or other async models that exist in C++, you need the fundamental guarantees. Your operation's always complete, and they don't have to be able to fail.
Yeah, but you get a lot of that from the model.
Yeah, right. The model like makes it surprising when you first hear about it. When I first heard about the model, I was like, that sounds wacky. That like these operations always have to complete. But when you start writing the code, you're like, oh, it's just easy and natural. It's just normal. And then it gets you so much expressive power that anytime you feel like it's awkward, sorting it out is so much lower of a cost than everything you get from the whole model that it's just like facially worth it.
Sorting it out exposes problems with your thought model.
Things that you thought were.
It's more likely you're confused.
Right, exactly, yeah. I like it when annoying problems turn out to be like reality reified in code telling me I was wrong.
Yes, I enjoy that part too.
We have any more questions?
I just made the close synchronous for what it's worth.
Oh. But in my defense, you can't do that for counting scope.
Yeah.
So we do have another candidate for asynchronous construction and destruction. Yeah. So
Do you have recommendations about what to do when close fails?
So that's a really interesting question, and I don't know if you were here when I had the conversation about IOU ring, because like event FD writes can actually fail.
Yeah, it's the same
Yeah,
thing.
and so can IOU ring. For me, in my entire programming career, I have always acted like close always succeeds. There are, and so I've acted like close always succeeds, and that's like wrong on two levels of analysis. So there's close always succeeds is right until it's wrong. Now let's say it's wrong. There's a partition of how it's wrong. It's wrong in that I could be secretly right, but close said it failed. There's a whole list of error codes it returns. It's like, I was just letting you know that like the last thing you did failed, but like I closed to the file descriptor. Right? And then there's like actual hard failures. And the only time I've ever really seen that was I was working on a high performance time series database that did a lot of work with memory mappings. And so we would have memory map back files. We would try and like do close operations that would unmap regions of memory. But in order to like take a region of memory that's like this and unmap this part of it, the kernel needs to allocate a structure to represent that new linked list entry, which can fail, and then close fails. And the way we reacted to that, of course, was we aborted the application. So I mean, it's close can fail, and so can like, so can IO ring up close, and so can IO U ring enter, and so can writing to an event FD. But the problem becomes when those like basic building blocks that you're relying on to give you the guarantees you need to reason about your program fail.
Right.
How do you actually react, right? The only argument I can muster is, people who are writing like horrific unstructured C code, right? Like think they can react, and they've never tested it, but they think that it's fine. And every time I've seen that happen, I'm like, well, if you do that, right, you just got a whole bunch of operations that never complete over here. You leaked all this memory, right? Maybe if
Worse
you
than crashing, probably.
yeah, right. Well, the other one is if you just accept that IOU ring enter failing means that like you're done and you don't abort the application, you're going to start returning and you're going to clean things up, but the kernel's still using that stuff, right? You don't know which operations it completed and failed to post the CQEs for, and like you can't reason about the universe anymore, and so you just kill the whole thing.
Docs.kernel.org says close failing should result in one of two things: application termination or ignore it completely. Those are your only two options.
Okay. One more question.
Yeah.
Is nested scope entering necessary, or should that be
So
done in the code?
the nesting, you mean the ordering?
Yeah.
Yeah, I don't think that I've ever needed it, but I wanted to express that it was possible.
For
Right.
locks, you need it.
Yeah,
You're definitely
but
gonna
should
get
it be
asked.
expressed in an algorithm, or should it be expressed in just the way you lay out your code? Like acquire this scope, then this scope, then this scope.
So
As we do
it
in-
is useful for syntactic reasons.
I mean, if you,
Yeah,
if you
it's
care
syntactic
deeply about the
shit.
syntax, senders and receivers is not the way to
but it's still
With
nice
the-
to have
with
a
the reflection,
code.
we
Like,
can
it-
turn a nice language into this.
It's like
The YouTube comments write themselves. Like
you. And also, expanding variadics.
Okay. Yeah.
Yeah.
Sure.
Yeah, because the like for example, the lifetime just forwards a variadic through to
Right.
what it calls enter scope, which is confusingly named because it's not always enter scope. It's only enter scope in like
Yeah.
simpler version that pre-selects it for you. But I've never had any reason to use it. I just when I was writing the paper, I was like, this is something people are going to want because whenever you go into a room that's full of people who are looking at your async model but don't write asynchronous code, right? They're like, wait, this doesn't work like synchronous code, and you're like, correct. And they're like, well, it should pretend it does. And so the nesting thing is part of that. And locks are a good argument for it. But interestingly enough, and I'm sure this will get pushback, construction of objects is not. Because when you're using lifetime, those objects can't gate references to each other until they're all constructed. Right? So like the kind of interdependence that normally you reify in synchronous code by having one line and then another one and relying on the destruction order, you don't normally experience that in the lifetime model. You'd have nested lifetimes if you wanted that. And the problem there is that there's no way to distinguish in the synchronous world between whether these sequentially constructed objects depend on each other or if I was just sequentially constructing them because that's the only tool that I have.
Right.
Oh, and in fact, the compiler can notice that and
Yes.
reorder them for you.
Yeah, Jonathan.
Like what you just said, with the construction can depend on each other, reminds me of like some like esoteric experimental language that someone is doing, but like essentially everything starts executing at the same time. So when you have like a function call, you start evaluating the function at the same time as you evaluate the arguments, and then because like you might not need the fourth argument until you're like halfway in the function, right? And so then only when you like block, you actually need the thing, and this is the sort of thing you can then express with senders.
Also, in some sense, like you have like work that's like detached in some sense, not necessarily like hard detached, but yeah.
Yeah, with
it's
your-
a full model though.
Yeah.
If you had actual dependencies, they would need to take the sender anyway, so you've
Yeah.
built up the graph.
Yeah, Ben.
We call that pipelining, but
Yeah. So simultaneous scope entering versus nested scope entering seems like that should be implementable with like when all versus let value or sequence. Right?
Yeah. The other reason to use
Except
nest,
that-
the other reason to use nest scopes is because if you want to achieve the effect of nest scopes without nest scopes, imagine that we ignore the variadic argument for a moment. You would do like within of the first one, and then return within of the second one.
Right.
And that not only is bad for compile times, but the error messages are even more unreadable than they already are. So that was one of the other motivations. Like if people want this, they can implement it in an isomorphic way, but it's a way that I think pessimizes compilation, readability of errors, nesting depth of like actual code written in their function. And so I decided I would just throw it out there. It was fun to implement, and it's not like particularly difficult.
Is it implementable with when all?
Nest scopes.
No, simultaneous scopes.
Simultaneous scopes is implementable with when all now that the paper that I showed has been adopted.
Okay. Including the destroying the scopes if.
Yes, so that was the reason the paper was needed.
Okay.
You can because entering a scope can
fail.
not complete successfully.
Right.
Combining it with a when
fails, you
all,
need to
yeah,
reverse the
yeah,
way.
combining them with a when all, and then like maybe you end up with a random set stop you didn't want. It matters for like this rigorous correctness, but it doesn't matter like for the concepts. Whereas if you do the same thing with exit scope senders, the reason I made that change and wrote the paper was I went to write like an async destructor, and I wanted to aggregate async destructors, and then my concept check was like you can't do that because all of a sudden when all made it able to send set stopped. So that was the motivation of that paper. Like most of this stuff was motivated by me digging in and checking for these extra completions I don't expect and seeing them pop out because people were like, oh, I'll just add an error completion anyway because I don't have to do all this metaprogramming. Yeah, so
that pisses me off.
I think we're out of time. So thank you all for coming.